Positional embeddings. So what are positional embeddings and what is this class token which this paper suddenly brought into the equation, right? So previously we saw how we could break an image into patches and then feed this into the model as features or slash tokens. I would still say we can call it tokens only once we add the positional embeddings to it, because essentially right now they are just features, right? They're not really tokens because the sequence is not very clear. So let's add this, but before we add positional embeddings, let's see what this class token is. So the basic idea which the paper says is essentially we want to do classification in the end, right? So the idea is that so let's say we have these patches and then we add positional embeddings to them, and what we'll look into that just now in a bit. Now, this classification token gets concatenated to all these tokens, and in the end, the model pools this token's output. It does not look at the other tokens. It just takes this token's output, passes that to a multilayer perceptron, and does the classification. So the idea is that this extra embed learnable token will carry a global feature context or something like that. So the CLS token is a learnable embedding used to gather global information from an image. So the idea is that this will have a global summary of what's going on in the entire process, and this is what is used for classification. And as usual, before we write the code, we should definitely build an intuition as to what's going on here. So this is where we were. We created these patches, and then we have understood that this resultant tensor is of dimension, batch size, features or tokens or whatever, and hidden dimension. And the dimension which we finally came upon is batch 196 and 768. So what does this even mean, right? This means we have 1, 2, 3, and so on up to 196 tokens, each of 768 hidden dimension, right? Now, the idea is we want to add one more token here. This will be the CLS token. This gets concatenated horizontally to this tensor. The resultant dimension of this will be batch size 196 plus 1 and 768. That is basically batch size 197 and 768. So of course, this token also has a 768 hidden dimension, just like all the other tokens. It's just the same thing. It's just a unique one which is not related to the image, because all these tokens are related to the image, but we are going to add this token which is not related to the image, but this will carry the global information. Now coming to positional embeddings. So the positional embeddings, generally what we notice is we have sine cos in transformers, but the authors of the paper suggest that instead of using sine and cos, if you can just put a blank zero initialized tensor of dimension, which is same as the tensors, as the input tensors, because they need to get added with each other, right? So the dimension has to be same. So if we can do a torch dot zeros of this dimension and concatenate and then add these two, sorry, not concatenate, add these two, and then we finally have our set of tokens that can be input directly into the transformer. So this is the intuition. Now let's look at the code. Let's see what's happening there. The code is very straightforward. What we do is we have a class called ViT input embeddings. Again, it inherits from nn dot module for obvious reasons. Now, the CLS token is an nn dot parameter of torch dot zeros of 1, 1, and config of hidden dimensions. The config is a config file, a JSON, which we'll pass later during training. Now, this first one is for batch size. This one is the token itself, the dimension of the token itself. And just like how other tokens, the image patches are 1, 2, 3. Similarly, this is 1, and this is 768 in our current scenario. We use this patch embeddings, which essentially we created in the previous video. And here, if you notice, we have set a variable called self.number of patches. That is image size divided by patch size into image size divided by patch size, the height by patch size and width by patch size. Now, that's what essentially results in 196, right? Now, number of patches is self.patch.embeddings.number of patches. Self.patch.embeddings is this, which is the class which we built in the previous video. And now positional embeddings is nn.parameter torch.zeros 1, comma number of patches plus 1 and config of hidden size. The +1 here is to accommodate for the classification token. The number of patches is 196 and +1 makes it 197, which is the classification token. And we have a dropout. That's what's mentioned in the paper. They said that eventually adding a dropout in the end helps trading and regularization, stuff like that. In the forward, it's straightforward. You get an input image. You see what the batch size is because dot shape of 0 will give you its first dimension. That's batch dimension. Image embeddings is self.patch embeddings of input image. That is this, the one which we created in the previous video. Classification token is equal to self.cls token.expand batch size -1 -1. -1 and -1 keep both the dimensions same. That is, this dimension and this dimension remains the same. But here we kept it as 1. We can now expand that to the batch size if we are going for a 4 or 8 or 120 or whatever. Now class and image embedding. That is torch.cat classification token and image embeddings along dimension 1, because dimension 0 is the batch dimension. Dimension 1 is the horizontal concatenation. Here we can see, as we said, we are adding these two together horizontally along the first dimension. So we need to mention that is dimension 1. Now, so the final embeddings after all the pre-processing is classification and image embedding gets directly added to the positional embeddings, which are of the same dimension as class and image embeddings, right? Because we said number of patches +1, which makes it 197 in our case. And this again gets passed through a dropout for experimental reasons. And this gets returned finally, that is final embedding with dropout. That is pretty much it for the intuition. This is where we say we are done with pre-processing. We can now move on to the attention and the more juicy part of building the ViT. But these parts are extremely essential because these pre-processings give you an intuition of how the tensor transforms and what is the journey the tensor has to take, where the initial value of the tensor is the image. And finally, we break them into patches. We add the classification token and how we add the positional embedding to all of this, and then add a dropout, and then we pass this to the model. That's it for the video. And in the next part, we can look at self-attention.